Hi, Charlie Pyatt here. In this video, I'm continuing my series on the design and exploration of mouse ergonomics. In the last episode, I introduced the Statial.b, an open-source adjustable mouse with movable surfaces that can be locked into position. This allowed the design to fit any hand size and grip style. The Statial was primarily a test armature concept for exploring mouse ergonomics, more of a tool than a finished product design. Now that I've been using it for a couple of months, I want to apply what I learned to a series of mouse builds. Beyond that, I think it's a great opportunity to explore alternative tracking technology for this build. Today, every modern mouse, from budget models to the highest-end gaming devices, relies on an optical sensor to track movement. But that wasn't always the case. Some of the earliest mouse input devices from the 1960s used a completely different underlying technology. Instead of tracking movement optically, these devices relied on magnetic fields to determine a mouse's position on a tablet. This style of input device was known as a digitizer, and the mouse itself was referred to as a puck. I don't want to get too deep into how digitizers work, but it's good to have an understanding of the basics of the technology to see how it could be applied to modern gaming mice. The core principle driving digitizers is electromagnetic resonance, or EMR. Instead of optical tracking, a digitizer relies on what's called an LC or resonance circuit made up of a capacitor and an inductor coil. When a charge is induced in the inductor coil, the circuit begins to resonate at a specific frequency. If the electromagnetic field of an LC circuit is induced into an adjacent coil, then the two circuits are linked by a phenomenon known as mutual induction. This setup has a few useful properties. First off, the two circuits don't need to be physically connected. Second, the distance between them can be determined by measuring the strength of the resonance signal. And finally, only one of the circuits needs a sustained power source to keep going. With a single pair of resonance circuits, I can only measure the signal strength, but not determine any sort of position in space. However, by stacking multiple inductor coils in a row, I can track movement along a single axis. If I have a second perpendicular series of coils, then I can track an additional axis. By combining both of these rows together in a grid, then I can track both the X and Y positions of a resonance circuit. I have an old puck example here, and you can see the coil inductor located at the front. When this is set on the digitizer tablet containing the grid of inductor coils, the puck's XY movement can be precisely tracked. Additionally, button inputs can be transmitted wirelessly by shifting the resonance frequency. This allows the puck to wirelessly communicate its button states. This technology evolved throughout the 1980s and was later refined into modern digital tablets, most notably by Wacom in the 1990s. These tablets featured a denser grid of inductor coils for higher sensitivity and tilt detection. Tracking the tilt of the stylus works by analyzing the shape of the magnetic field. When the stylus is perfectly vertical, the field appears circular. As the stylus tilts, the field becomes more elliptical, allowing the tablet to calculate the exact angle of the pen relative to the surface. I wanted to revisit using EMR technology in a modern mouse form factor because it aligns so well with many of today's market trends. Since the circuit inside an EMR mouse is incredibly simple, the mouse itself can be ultra lightweight. Additionally, it doesn't require an onboard battery, further reducing the weight and eliminating the need for charging or ever plugging the mouse in. Beyond the weight savings, an EMR mouse offers capabilities that would be difficult or even impossible to achieve with a standard optical mouse. For example, it can detect yaw or twisting motions that can be mapped to leaning in a first-person shooter. Additionally, lift height can be easily adjusted, whereas it's fixed by the lens configuration in an optical mouse. One of the most compelling advantages of an EMR setup is that all the expensive components are housed in the tracking base, making the individual mice inexpensive to produce. From an industrial design standpoint, this opens up a bunch of exciting possibilities for creating more niche ergonomic mice without the usual cost barriers. The build plan for this project starts with using the Statial.b to explore ergonomics, then 3D scanning it into CAD to adapt those layouts to an EMR mouse. Finally, I'll 3D print and build bodies around the existing EMR devices to test everything out. I'm going to be working backward through that list, so my first step is finding a donor EMR stylus device to build around. After some research, I landed on the Wacom Intuos 4 released in 2009. It has all the features I need, is still widely available on the second-hand market, making it cheap to buy, and remains mostly supported by modern operating systems. As a bonus, the Intuos 4 originally included a mouse as an optional input device alongside the stylus. I can retrofit the Wacom mouse into my new design and refine it from there. I ordered a couple of Intuos 4 tablets and mice on eBay and got going on the teardown. I started by removing the back screws and cover. If you can see, it's really just one massive PCB. The induction coils are just traces running back and forth. One side of the board is vertical traces that track left and right x-axis movement, and on the other side of the board are horizontal traces that track vertical Y position of the stylus. The additional inputs, displays, and rotary selector are connected with FlexPrint circuits and can be disconnected until I need them later on in the build. Now onto the mouse. This is a great design for what I'm trying to do and has all the modern inputs I want in a left, middle, and right mouse button, front and back buttons, and a scroll wheel. You can see on the bottom there's no optical sensor, just a flat base with felt pads to protect the tablet surface. As I open it up, you can actually see they added a weight on the inside to give it some heft, which is kind of funny. Adding weights was a common practice in the 80s and 90s to keep electronics feeling heavy and expensive. The inside circuit is extremely simple, with a LC coil held at an angle and a simple controller board. The button and wheel inputs are controlled by the IC on the board. This steps the resonant frequencies up and down whenever a mouse button is pushed. The frequency change is detected by the base tablet and interpreted as the matching button press. There's also an adjustable trim capacitor over here. This is to tune the mouse into the right frequency range after the manufacturing and assembly process. This whole thing is all extremely old school analog, but it's a really efficient design. The one thing I don't like about it is the board size. This PCB is pretty massive and there isn't anything useful over the majority of it, just dead space and weight. I think what I'm going to do is physically cut down the board to be much smaller. From there I can solder my buttons and rotary encoder directly onto these vias. This will massively decrease the board size and make designing around it much easier. With that decision made, I mapped out the traces on the mouse that I'd be tapping into. With those done and color-coded, I can mark out how much of the PCB I'm going to trim down and cut it away with a Dremel. Now that the hardware is isolated, I can start working on my CAD workflow. I'm going to start in Fusion for all the static engineered components before exporting some of the elements into Rhino and Grasshopper for the generative design parts. I decided to redesign the base tablet PCB in a custom body. Could have kept it in the original injection molded housing, but I thought it would be more interesting to redesign everything so the mouse and base were visually connected. For the base tablet, I'll cut out a sheet of HDPE for a low resistance mousing surface. To give it a modern look, I'll add colored LED strips along the edges and within the controller ring, along with transparent bezels to let light spill out through the sides. Now onto the mouse design itself. I'll actually be creating multiple versions of the design based on the Statial.b input scans. To keep things simple, all the mice will share a common base with interchangeable top sections for customization. Additionally, I'll need to create components to hold the mouse switches and define cutting elements for the next stage in Rhino and Grasshopper. To keep all the internals clean, I designed a thin-walled cap to enclose the PCB and coil. I've modeled the cut-down PCB in from the last step and included a rod to hold the induction coil at the correct angle. With everything set up, I'm ready to export everything as step files and move on to the next phase of the build. Before modeling out my custom mouse caps, I need to scan in some references from the Statial.b. Over the last few months, I found myself using two primary configurations that best fit my grip style. I tend to use a palm grip, so both designs are similar in overall size. My finger positioning is a bit unconventional, where I switch between a 131 and a 122 grip. A 122 grip is the most common grip type. The thumb rests on the inside of the mouse, the index and middle fingers sit on the left and right buttons, and the ring and pinky fingers rest on the outside. A 131 grip shifts things slightly. The thumb is still on the inside, but now the pinky is on the outside, while all three middle fingers rest on the separate buttons. I prefer this grip when working in 3D software and CAD since the middle mouse button sees heavy use, often in combination with the right button. I set the Statial.b up in each layout and use my RevoPoint Mini to scan them in. Statial.b is right at the upper size limit of what the Mini can effectively capture, but the results turned out great. The lattice structure on the Statial.b helped with the scanning process, with each little node in the pattern acting as a natural tracking point. This allows the scans to be merged super accurately. The natural dark gray color of the prints was also ideal for blue light scanning as well. Now that I've imported my solid parts from Fusion and have my 3D scans, I can start creating a Grasshopper definition to generate my custom mice. To create this base geometry, I'll first align the components with their corresponding positions from the input scan. I need to generate geometry that envelops the base, left, right, and middle buttons, as well as the left, right, and rear surfaces. While the base will remain fixed in place, the positions of all the other parts will vary with each version of the Statial.b scan that's imported. Then apply a shrink wrap process to merge everything into a single shape. Shrink wrapping works by simulating a physical tension on a mesh, and then using the input scan parts as collision objects. After the simulation runs, I'll get a smooth unified geometry that wraps around all my components. Next up, I experimented with some tileable geometric patterns for the back section of the mouse. Since the back of this mouse is mainly there just to support my palm, I can cut out most of that surface with any pattern I choose. I tested various patterns and sizes before settling on a few I liked, and then applied them to the back of the mouse. After that, I used the Boolean objects I imported from Fusion to finish the cutting and bracket placement. These components will integrate into the sidewalls of the mouse to hold my switches while allowing the buttons to flex. Figuring out the order of operations for all the cuts and unions was a bit tricky, but after some trial and error I managed to dial everything in. With that, the mouse shell is nearly complete. The Grasshopper system I've built now allows me to import any configuration of my Statial.b and then generate a custom static mouse shell. With the geometry generation done, I exported everything as STLs over to my Formlabs Form 4 resin printer for my first round of test prints. From a mechanical standpoint, everything worked out pretty well on these. I'd made so many minor adjustments in Fusion and Grasshopper at this point that the details have been pretty well figured out. For painting, I had some color directions in mind, but to be honest, this whole first round just didn't go well. I skipped doing any sort of visualization or rendering options, just went for it, and ended up really not liking the results. I pretty much scrapped this whole first set of painted prints and went back to the drawing board by doing a proper set of test renders to get my color material and finish figured out. Getting fixated on the end of the project and not doing the design process like this is an easy situation to fall into and almost always ends badly. In any case, I went back and did a whole series of renders to dial in the material and finish, and ended up going with a translucent top and a solid color base. This concept would connect the generative idea of the top of the mouse and the solid repeatability found in the lower section. I like the idea of being able to see an obscured view of the mouse switch and components through the body as well. With the design direction put back on the right track, I reprinted the parts and did a reassembly of everything. For the solid components, I used a high-build rattle can primer and wet sanded everything back down to 800 grit before applying a final layer of paint. Gave the parts a matte clear coat finish instead of a gloss like on the first round, which I think gives the parts much more of an interesting soft touch kind of look. For the clear parts, I wet sanded them down to 600 grit and just hit them directly with the matte clear coat. The scuff surface with the matte clear gives them a translucent appearance. This is great because it hides some of the surface imperfections on the print. I can't get into a lot of the interior geometry for sanding, and if I had applied a gloss to it, it would have highlighted every surface imperfection I missed. Finally, I hit some of the detail components with a translucent purple. This almost gives those parts a hard candy look and plays with the other colors and opacities really well. Now that all the parts are painted, I can move on to the final assembly. I started this off by putting together the stylus base. I've already assembled the translucent bezel and given it the same finish as the upper custom mouse bodies. The 3D printed side panel that will cover the button inputs and micro displays from the original Wacom gets glued on first. The new scroll dial and the LEDs for it go on next. For the LEDs, I'm using WS2812s on a circular PCB mounted behind the scroll dial with some additional LED strips above and below the Wacom. You can see I've already attached the 1/8 inch HDPE sheet to the bezel and side panel. I've also put on some additional 3D printed parts with captured machine nuts that let me mechanically attach the big Intuos EMR PCB to the rest of the assembly. For wiring the mouse, I started by connecting together all the various components. This process was almost identical to what I did for the Statial.b. I'm just direct soldering the wire to my mouse switches and rotary encoder. These wires need to pass through a slot in the top cap of the mouse, so I just used GST-PH connectors here. This would let me fully disassemble and reassemble the mouse without having to do any resoldering. Getting the connector wires into the vias on the PCB was really tricky because they were so small, but it all came together with a little patience. Here I'm greasing the mouse wheel and installing the rotary encoder. The encoder is held in that little arm there. The wheel, arm, and encoder all deflect down and hit the middle mouse switch when pressure is applied. All that was left was to stick some mouse skids on the bottom, and then I just press fit the switches into their brackets on the translucent mouse top to complete the assembly. Now I finally get to the fun part in the testing. It was really strange seeing this older technology being repackaged into a modern gaming mouse. The weight ended up being a little higher than I would have liked for a working mock-up at around 50 grams, but I calculated the production weight to be closer to 35 grams or less, which is pretty insane for a full-size wireless mouse that never needs to be charged. I really like the way the base came out too. The translucent HDPE gives a really nice lighting effect. Across the board, this whole design ended up messing with depth and clarity in both design and material, and I'm really glad I pushed through and finished it up. Hope you enjoyed the build, and I'll see you next time.